Today we are going to do application of line integrals, and this application is something that you probably have seen before, and it is called potential theory. Okay, so the idea is, suppose you have a force F acting on a body. Okay, suppose you have a force F acting on a body, and due to this force the body is displaced by a distance dr. Okay, then the work done in this process is dw, which is a scalar, which is F dot dr. So this is what you learn in your standard mechanics course. We are assuming that this dr is an infinitesimally small displacement, and for this infinitesimally small displacement dr, the force is a constant. Okay, so now what happens when you take a body from one point to another by application of this force? So we look at specific example. Suppose you have a gravitational force. Okay, now so the body is attracted towards the ground. Okay, and the force on the body is just the mass of the body. So mass of the body and times the acceleration due to gravity, and it's acting in the minus k direction, that is, it's acting downwards. Okay, so we assume that this is the plus k direction, this is the force that is acting downwards. And suppose you assume that you're displacing the body by some amount. Okay, then if this displacement of the body is given by dzk or dyj, okay, then you'll say that F dot dr equal to mg dz minus mg dz. Okay, so if your dz is negative, then the force does work in pushing the body down. If your dz is positive, that is in the upward direction, then you have to do work to push this body. So what we assume is that this is a z direction and the force is acting on this direction. mg times. Okay, so if dz is negative, then you have to do work. Okay, whereas if dz is positive, then the force or sorry, if dz is positive, you have to do work. So the work done by the force will be negative. Okay, and if dz is negative, then the force does work. So it is going down, and the force is doing work of mg times dz. Okay, now this is an example of a force which is constant everywhere. So if I'm looking at this body, if I'm looking at this piece of chalk, okay, it's and I leave it, it will drop down by gravity. Now it does not matter whether I'm here, wherever I am, the force is the same. So the force is independent of where you are in space, and so in this case, if you're doing work in going from a point A to a point B, then this is just the total work done in going from A to B is just the integral of dw. Okay, and the integral of dw in this case will just be integral F dot dr okay, from A to B, and this will just be equal to, since f is a constant, you can take it outside the integral. So it is just f is just mg into minus k hat dotted into integral dr or integral dz or dr from A to B. Okay. Now if this point A is denoted by coordinates xa, ya, za, and this point B is denoted by coordinates xb, yb, zb. Okay. then the value of this is just mg minus mg dz from za to zb. So, it is independent of xa and ya, and this is just equal to minus mg. Okay. So what we found was that you can calculate the work done by this force in a straightforward procedure. Now, in this case the force was constant everywhere. So, it was the same force. So, you could take it outside the integral, and this integral of dr just became a straightforward r at the boundaries. Okay. It was just the value of r at the boundaries, and since you had a dot product, we just needed to worry about the z component. Okay. Now, but there are many cases, many situations in which this force might not be a constant. Force might depend on where you are. Okay. So suppose you have a situation where the force at this point might be different from, say, the force at this point, or it might be different from here, and so on. Okay. And so this implies that force is a vector field. So force depends on x, y, z. So force is a vector field, and it has components Zi. Okay. So the force is given by this vector field. In this case it was just a constant. So these two components were 0, and this was equal to minus mg. Okay. So if force is a vector field, then what happens to this integral? And the answer is fairly obvious. So then your w just becomes integral a to b, okay, f dot dr. And one point that we have to mention here is that even in this case we moved along a path. Okay. In this case also we moved along a path. Okay. But since only the z coordinate was changing, the path was just you could just think of the path as depending on the final and initial states. In this case, it depends on which path you are taking. Okay, so you are going from point A to point B along a certain path. If I show the displacement, so you have a dr, okay, and this dr is part of this path. So you are going from A to B, point A to point B. These are 2 points in 3-dimensional coordinate space. And this is the path which is called C. Okay, so this is the path C, and you can clearly see that the work is nothing but a line integral. Okay. Okay. Now you might ask when does this line integral depend on the path? So suppose I go from a different path. So if this is C1, this is C2, is the work done the same or is it different? Okay. So is W dependent on path? So you start at the same initial point and start at the same and you end at the same final point, but you ask the question, is the work done by the force dependent on which path you take? Okay. And the general answer is yes, it depends on which path you take. There are certain kinds of forces for which this work is independent of path. Okay. And this is what we want to explore in this lecture. Okay. So So now we want to say that this work done in going from A to B, it may or may not depend on the path, and in some cases it depends, and in some cases it does not depend. And so if you ask what is the feature of F, okay, what is the feature of this force field that makes it path dependent or path independent? Okay. So that is what we are going to explore in the next few minutes. So you notice that the force is different at each point, okay, and so if you want to calculate the work, you have to do this line integral. Okay. Now okay, suppose W was independent of path. Okay. So suppose this word W was independent of paths taken. Okay. So what happens in this case? Now you say that the work done in going from here to here is the same as work done in going from here to here. Okay. Now so you say that integral over C1 f dot dr is equal to integral over C2 f dot dr. Okay. And this implies integral over C1 f dot dr equal to minus integral over C2 prime f dot dr. Okay, so this is from A to B, this is from B to A. Okay, so what is the C2 prime? So C2 goes from A to B along this path. C2 prime goes from B to A backwards along the C1 path, along the C2 path. Okay, so if C2 is in this direction, C2 prime is in this direction, and the limits of integral are from B to A. And it's fairly obvious that that this integral going from A to B of f dot dr along C2 should be negative of the integral going from B to A of the same f dot dr. Okay, so this implies now this implies that the sum of work done in these two paths is 0. So integral, so the first path you go from A to B along C1, and then you go along C2 prime from B to A. So the total work done in this path is 0. So it's the sum of these two. So that is 0. So what you get is that the closed integral of f1 of f dot dr. Okay, so is equal to 0. Okay, so and you can show that this is true for any two paths. If f is if this work is a path independent function, then any path you take, any closed path you take, then the work done should be 0. So work done in any closed path should be equal to 0. Okay. Now since this is true for an arbitrary closed path, okay, we can use Stokes theorem to say that this closed integral is equal to, if this path, you can take a path that encloses a surface d sigma, okay, then you can say that this is equal to integral over the surface S of del cross f dotted into d sigma. Okay. So this is true for any closed path, and so we can use Stokes theorem to say that this is equal to the curl of the force field, or the integral of the curl of the force field over this surface. Okay. Now since we said that if work is a path independent function, you can choose any path, and so your surface can be completely arbitrary, and so if this is to be true for all possible surfaces, then this implies del cross f equal to 0. So the condition for path independence is del cross f equal to 0. Okay. Now, it is important that del cross f should be 0 in the entire region. Okay. So, in the entire region. Enclosed by the path. Okay. So, enclosed by all the paths considered. Okay. So I'll just explain why I put this qualifier. It could be that W is path independent in one region. It could be that W is path independent in one region. So in this region, your work could be path independent, whereas outside it might be path dependent. Okay. So therefore, the condition is that we are restricting ourselves to this region where the work is path independent, and so everywhere in this region the curl of f should be 0. Okay. So wherever the work is path independent, the curl of f should be 0. Okay. And this leads to the condition, it's if you dou fx by dou y and these are the components of the curl, and so each of the components should be equal to 0. Therefore, you have these identities. Okay. So the fact that your work done is path independent implies that the force field has to satisfy these conditions. So if you take any arbitrary force field, okay, then it need not satisfy this condition, but if it does satisfy this condition, then it is indeed path independent. So the work done will be independent of path. So let's take an example. Okay. Okay. Suppose I take 3x square y I f of x y is equal to 6 xyj. Okay. So suppose I take this as a force field. Now here I have restricted myself to a two-dimensional problem instead of the full three-dimensional problem. But if you take this as a force field, then you can see that six xy dou fy by dou x is equal to 6x, and these are not equal to each other everywhere. Okay. So if you consider any arbitrary region, the work done by this force in different paths will not be the same. Okay. On the other hand, if you had f of xy is equal to 3x square y plus okay. Now if I take the derivative of this with respect to y, I will get 6x. Oh, sorry, this with respect to, if I take the derivative of this with respect to y is that's a correction, I should get 3x square, and if I take the derivative of this with respect to x, I should get 6x. Okay. Now, if I take 3x y square plus, and make it 3x square y. Okay, so if I choose this function, then the derivative with respect to y is 6xy, and here the derivative with respect to x. So, if I differentiate with respect to x, this term contributes 0, this term contributes 6x into y. Okay. So it is equal, and therefore, this will be path independent. Okay. So, this leads us next to what is called as potential theory. Which states that suppose I have an f that can be expressed. So, suppose there exists, if for a given f there exists v of x, y, z, here f is also a force field such that f is equal to gradient of v. Okay. So, if there exists a scalar field such that if I take f and if I take the negative gradient of v, then I get f, then f is path independent. Okay. And the negative is just out of convenience. You could always, I mean, the negative sign is not really important in this case. It is just that v is usually defined as the potential energy, and the force is defined as the negative gradient of the potential energy. So the point is that if there exists a v such that f is minus grad v, then the force is path independent. Okay. So how do we understand this? Now we can say that we look at integral f dot dr, okay, from a to b. Okay. This is equal to, now if f can be expressed as minus grad of this, then this is minus integral a to b. Now f is minus grad v, so minus dou v by dou x, dou v by dou xi plus dou v by dou y j plus dou v by dou z k. This whole thing is dotted into dr. Dr has dxi plus dyj plus dzk. And we can go ahead and do the dot product, and we will get minus integral a to b dou v by dou x dx plus dou v by dou y dy plus dou v by dou z dz. And v is a function of x, y, z. Okay. If v is a function of x, y, z, this is nothing but the total change in v. Okay. So if v is a function of x, y, z, then dv is the partial with respect to x times dx plus partial of v with respect to y times dy plus partial of v with respect to z times dz. Okay. So this whole thing is nothing but dv, and so the integral will just give you minus v of b minus v of a. Okay. So the point is that if your force can be expressed as a negative gradient of the potential, so if there exists a function v such that f equal to minus grad that, then the total work done in going from a to b is just the difference in potential energy. Okay. And this is something that we have seen before. Suppose I want to know how much work I need to do to lift this chalk, then you say that the difference in potential energy out here it is mg times the height there, out here it's mg times the height here, and that difference gives you the work done by this force. Okay, so now the point is that if f is path independent, okay, it can be expressed as a gradient of potential, and vice versa. If f is expressible as a gradient of potential, then it is path independent. Okay. Now this potential theory is something that has a lot of applications in different areas, and even the idea of path integral path independence is something that we encounter frequently when we are in thermodynamics, when you calculate the pressure volume work done in changing the state of a gas under various conditions. Okay, so now this when we say that the force is negative gradient of potential, we should always be a little careful when you write this. Okay, and just to illustrate this point, I'll take an example. Okay, suppose there is a system of two particles. Particle 1 is located at R1, that is x1, y1, z1, and particle 2 is located at x2, y2, z2. Okay. And typically, if you look at the potential energy will be a function of the positions of both the particles. So the potential energy is the energy that the system has on account of the position of the particles. Okay, so the potential energy will be a function of x1, y1, z1, x2, y2, z2. Okay. So in general, if you write any potential energy of the entire system, it should depend on where each particle is located, not just where one particle or not just where the second particle is. It should depend in general on where both the particles are located. Okay. Now you can ask what is the force, and if somebody asks what is a force, then you should ask the force on what. Okay. So now if you ask what is the force on particle 1, so this is the force on particle 1. Okay. Now the force on particle 1 is given by minus gradient with respect to R1 of V. And this is equal to minus dou V by dou x1 I plus dou V by dou y1 j z1 k. So this is the force. This is the force on particle 1. Notice I am taking a gradient with respect to x1, y1 and z1. Okay, so only the coordinates of r1 are involved when you calculate the force on particle 1. Similarly, when you calculate the force on particle 2, it is a gradient with respect to r2 that appears, and this is okay. So you should always be careful when you write the force. You should not simply say it's a gradient of a potential. It's what you really mean is a force on one particle, okay, is a gradient with respect to the coordinate of that particle. Okay. Now if you just have a system of just one particle and you just have a force field for f of x, y, z as we had in the previous case, then the force can be thought of as the gradient of the potential. Okay, but in all other cases you have to be careful. You have to say the gradient with respect to which coordinate. Okay, let's look at a particular kind of force which is very common. In fact, it's the most commonly force that you encounter in various areas of chemistry. Now, in most cases, the particles 1 and 2, the force between them, okay, the value of the force just depends on the distance between the particles. Okay, so what I mean is that if the potential energy of the system, the total potential energy of the system, if the only contribution to potential energy is due to the interactions between the particles, okay, so if only contribution to potential energy is due to interaction between particles. So, if the only contribution to the potential energy of the system is due to the interaction between the particles, and that means the particles are not in any external field or anything. So you assume that, let's say, if you have two charged particles, then the only force is due to the attraction or repulsion between these charged particles. Okay. You don't have any other contribution. You don't have an external electric or magnetic field. You don't have any gravitational field or anything else. And this is a case that we typically encounter in various areas of chemistry. For example, if you take the nucleus and the electron of the hydrogen atom, the only interaction is due to the the only contribution to the potential energy is due to interaction of the electron with the nucleus. Okay. So in such a case, your potential energy, which depends on the coordinates of both the particles, okay, can typically be expressed in this form. So, if you had two particles and they are and it's only the potential energy is only due to the interaction between the two particles, then the potential energy is a function only of the distance between the particles. Okay. Such a potential is called a central potential. Okay. And in fact, most of the potentials that we know, whether it is gravitational potential of two bodies attracting each other due to gravitation, or the Coulombic and the electromagnetic forces between bodies, they are all in the form of central potentials. Now, in case you have a central potential, then what happens is that if you take dV by dx1, so dV by dx1 is equal to partial derivative of v with respect to r times partial derivative of r with respect to x1. Okay. Now, you can see that partial derivative of r with respect to x1 is nothing. So this is dV by dr, and I will just call it v prime. Okay, v is only a function of r. Okay, so I can write it as v prime. This is the derivative of this function. Okay, times dr by dx1, and if you calculate that, you will get this will just turn out to be x1 by r, or rather x1 minus x2 by r. Okay, so if you take d by dx of this quantity, it's 1 over twice square root of this 1 over twice r times 2 x1 minus x2. Okay. And if you calculate dV by dx2, this will come out to be dV by dr times dou r by dou x2, and dou r by dou x2 is minus of this quantity because you have a minus sign in front of x2. So, this just turns out to be V prime into minus x1 minus x2 by r. Okay. And you can take this argument through and you can show that the force acting on particle 1 will be the negative of the force acting on particle 2. Okay. So, the forces on the two particles are opposite. So, for F1 equal to minus F2. So, this implies okay, so forces are equal and opposite. And this is a characteristics of this central potential. So, when you have a central potential of interaction between the two particles, then the force on 1 due to 2 will be equal and opposite to the force on 2 due to 1. Okay. Now, let us do an example where we calculate a line integral, okay, of a certain force along two different paths. Okay. So, the force is given by f of x y. This problem is in two dimensions, x y I minus x square j. Okay. And you calculate the work done in going from the point 1 0 to minus 1 0 along two paths. The first path C1 is a semicircular path C1, and the second path C2 is a path along the x axis. Okay. Okay. So, calculate the work done in moving the particle from 1 0 to minus 1 0 along these two paths. Okay. So, if you were so the first thing you will check is f path independent, or is work path independent. Okay. And in order to check that, you take the y is equal to x to x. So it is not path independent. So, in general the work done is not path independent. Okay. So, now let us calculate the work done. So, the work done is integral over C1 f dot dr from 1 0 to minus 1 0. Okay. So, now in this case what you will say is that this is equal to zero, and here dr in this case will have two components. It will have dx and it will have dy. So and if I substitute for this is xy dx minus x square dy. And remember, dx and dy are not completely independent because we are going along this path. Okay. And so along the path, along C1, we have x square plus y square is equal to 1. So, we have x square plus y square equal to 1, and therefore, we have 2x dx plus 2y dy equal to 0. Okay. In other words, dy is equal to minus x by y dx. Okay. So, the rate of change of y along this path is related to the rate of change of x along this path, and moreover y is also related to x. Y is equal to square root of 1 minus x square. Okay. So, putting all this together, we will get this as integral from 1 0 to minus 1 0. So, the first term x, now y is square root of 1 minus x square, okay, dx. The second term is minus x square. Now, dy is minus x by y. So, minus x by square root of 1 minus x square dx. Okay. So, I can take all this together and I can write this as integral. Now I do not have to worry about y at all, because I have already taken into account that y is along this path and the rate of change of y. Okay. So, then I can just write this as integral 1 to minus 1 of x square root of 1 minus x square plus x cube divided by square root of 1 minus x square dx. Okay. And you can go ahead and work out this integral. Okay. It is fairly easy to show that the value of this integral should be 0, because you are integrating from 1 to minus 1, okay, and the integrand is an odd function of x. So, if I change x to minus x, then the integrand changes sign, and therefore, this is equal to 0. Okay, so, you can evaluate this integral and you will get it equal to 0. Okay. Now, suppose you go, so therefore, you will say that integral over C1 f dot dr equal to 0. Now, what about integral over C2 f dot dr? Okay. And you can go ahead and you can follow the same procedure. So, you write your path. Now, so along C2, y equal to 0. Okay, so along C2 the y component is 0 and dy equal to 0. Okay. So, if you substitute these two, then you come back to your f. Okay. So, the only part that will contribute, since dy is 0, only this part will be non-zero, and here too y is 0. So, since y is 0, you just have integral, and this will be 1 0 minus 1 0 x into 0 dx minus x square 0. Okay. So, this is equal to 0. Okay. So, each of the terms is 0, and therefore, this whole integral gives you 0. And what you notice is that even though your function, even though the derivative said that the work should be path independent, the work done along these two paths is identical. Okay. So, the point is, work done along C1 and C2 is identical. Okay. Now, this does not mean that the work is a path independent function. What it means is that these two are just special paths where the work done is the same. However, if you take any arbitrary path, the work done will not be equal to this, or it won't be equal to 0 for any arbitrary path. Okay. So, in general, this is not a path independent function, but for these two paths, the calculated work turns out to be the same. Okay. Now, just one more thing I wanted to mention about this is along the path C1, so along this path C1, we calculated the work by using the equation the semicircle and substituting for y. Now you could have done this in plane polar coordinates. Okay, and I'll just illustrate this because this is a trick that will be used quite often. Okay, so often it's easier to solve some integrals in plane polar coordinates, and especially when you have a path that traces out a circle, then it's better to go to polar coordinates. So how would you do this integral in polar coordinates? So first thing, you'll write f dot dr from integral xy dx x square dy along C1 . Okay, so in polar coordinates you say x equal to r cos theta, y equal to r sin theta, okay, and along the path C1. So along C1, we notice that dr equal to 0. So along this path, your distance r theta. So this distance r does not change. Dr equal to 0, r equal to 1. Okay, and theta goes from 0 to pi. Okay. So then what you can write is that x equal to cos theta, dx equal to minus sin theta d theta, y equal to sin theta, dy equal to cos theta d theta. So the entire curve C1 is just parametrized by a single variable theta. So instead of changing both x and y, you just change theta from 0 to pi and you trace out the entire curve C1. Okay. So you substitute this over here, and what you will get is integral x into y. So that is cos theta minus sin theta, and dx is so cos theta sin theta minus sin theta. So you get cos theta minus cos theta sin square theta d theta, and this next term is minus x square. X square is cos square theta into cos theta. So that is cos cube theta. Theta from 0 to pi. Okay, and if I take the cos theta common, then I have, so this is equal to integral cos theta sin square theta plus cos square theta d theta from 0 to pi, and this whole thing is just equal to 1. So this is integral of cos theta is sin theta from 0 to pi is equal to 0. Okay. And what this illustrates is that going into polar coordinates is one way to do this integral, and you can imagine that if you had a more complicated function, then doing it the other way in the xy coordinates might not be as simple, whereas going to plane polar coordinates, we can do it even if we can calculate this integral even if these are more complicated functions. Okay, even if we had more complicated functions here, we could calculate this integral much more easily in polar coordinates. Okay, so the last thing I want to show is an illustration of Stokes theorem. Okay, so let's look at f is equal to y square I minus x square j plus 0 k. Okay, so now you are asked to calculate. You are asked to calculate the closed integral along C1 and compare it to the area integral over S. Okay. So you are asked to calculate integral f dot dr along C1. Okay. This is a closed loop. So closed loop along C1 and show that this is equal to integral del cross f dot d sigma over S. Okay. So this is what we are going to show, and in this way we are going to illustrate Stokes theorem. Okay. So now this line integral is something that we should be able to calculate easily. Again we'll go to polar coordinates. So this line integral will be equal to integral. Now y square is sine square theta, and what you'll have is sine square theta dx. So dx is minus sine theta d theta. Okay, and the limits of integration of theta, if this, let's assume that this is a unit circle. Okay, so the limits of integration of theta are from 0 to 2 pi. So now you have to go a full circle. So that is the limits of integration of theta, and the other term is minus x square is cos square theta, and then you will have a dy. Dy is cos theta d theta, and you are integrating again from 0 to 2 pi. Okay. Now both sine and cosines are periodic functions, and so sine square and sine cube are also periodic functions of 2 pi. So this integral is equal to 0. So because sine, so the area under sine function from 0 to 2 pi is, and if you take sine square, sine cube will look like this. So it will have a plus part and a minus part. Similarly, cos cube will also have equal plus and minus parts. So both these integrals work out to be exactly equal to 0. Now if you calculate the surface integral, so in order to calculate that, we look at del cross f. Del cross f is k into, and if you calculate this, you will get an answer of minus 2x minus 2y. Okay, so you can take the curl of this force field and you will get this answer. So since the vector is in the xy, since the vector field is localized to the xy plane, the curl will be localized to the z direction. And now what you have to do is you have to calculate the surface integral. Now the surface integral, you have to put the limits carefully so that you trace out the entire circle. Now d sigma is equal to dA. So it is the area times the normal vector. Now the normal vector to the surface is along k. So it's dA times k hat. And your dA in plane polar coordinates can be written as r dr d theta times k. Okay, so dA in polar coordinates is dA in Cartesian coordinates. This is equal to dx dy. In polar coordinates, this works out to be r dr d theta. Okay. So if you put this together, what you get is del cross f is equal to And now your area integral, you have to integrate over this entire area, and the way to do that is to have integral. So del cross f dot d sigma. So you have 2x minus 2 r cos theta minus 2 r sin theta. Okay, that is minus 2x minus 2y. I wrote in polar coordinates, and instead of dA, what I have is r dr d theta, and I have to integrate both r and theta to get the full area integral. So I have to integrate over this entire area, and that corresponds to r going from 0 to 1 and theta going from 0 to 2 pi. Okay. So that corresponds to the entire area. And you don't need to do too much work. You can just do the theta integral. It is just cos theta, and cos theta and sin theta. When you integrate from 0 to 2 pi, you just get 0. Okay. So this illustrates Stokes theorem, and what it also illustrates is that when you calculate these surface integrals or line integrals, you have to use the best method available, and sometimes it might be polar coordinates, sometimes it might be Cartesian coordinates, and you have to put the limits very carefully. Okay. So notice that it was very easy to give the limits in polar coordinates. Now if I was using Cartesian coordinates, then the limits of x goes from minus 1 to 1, but y goes only from here to here. Y does not go from minus 1 to 1 in general. If I had put x going from minus 1 to 1 and y going from minus 1 to 1, then I would have gotten a square area. Y. So you have to be very careful when you put the limits of integration. Y only goes from minus square root 1 minus x square to plus square root 1 minus x square. Okay. So it's usually a slightly more tricky problem to do this in Cartesian coordinates. Okay. So in the next class we'll change gears and we'll go to matrices. Okay. So I hope these lectures on vector analysis have been fairly simple to understand. Okay. It's important that you try a lot of different problems, and especially when you calculate line integrals and area, surface and volume integrals, some of the techniques you learn as you practice more. So it's important that you get a lot of practice by doing various solved examples. Okay. Thank you.